Welcome back, ladies and gentlemen. In this video, we're talking about Newton's universal law of gravitation. And this is coming on the heels of looking at Kepler's laws of orbital motion. And so we want to kind of recall what Kepler was saying. That if we have finger out of the way. Sorry. You have a planet orbiting the sun, let's just say. There is a radius to that orbit, and even if it's not a true circle, if you consider an ellipse, then there would be an average radius, even though it changes, so there's an average. But what Kepler was saying, his descriptions of orbital motion focus on how a planet's distance from the sun affects orbital speed and orbital period. So how the radius is going to affect the orbital speed and the orbital period, capital T, right? Well, that's what Kepler focused on with his laws of orbital motion. What Newton focused on instead with the law of gravitation is force and acceleration. Recall that what we've learned about Newton's second law of motion, and really it started out just F equals ma. Okay. And this really is net force. Well, using Newton's second law to find the weight of an object, the force of gravity acting on an object, we simply said that force of gravity is equal to the mass of the object times gravitational acceleration, or you could say the acceleration due to gravity. But Newton actually didn't write it this way, at least not at first. We're going to see later on why g is 9.8, but we're not going to get into that right now. Newton realized that for a larger planet, let's look back at this diagram. If you had a larger planet orbiting the sun, then it would take a larger force to produce the centripetal acceleration. Remember that, centripetal acceleration toward the center of the circle. It's going to take a larger force if the planet has more mass. And so as the mass increases, the force does, just like it does here. But what Newton also realized was that if the planet was orbiting further away, if the distance away from the sun was greater, so for a planet over here, where radius is larger, then the force would be weaker because of that increased distance. So the force would be weaker, force would be smaller, further away from the source. So what Newton ended up coming up with is this law, this description for gravity as a force. And this description is in the form of an equation. And so here we go. Force of gravity is equal to g times the mass of object 1 times the mass of object 2 divided by the radius between the two objects squared. That is, right there, Newton's law of gravitation. So we're going to break that down and look at all the important business that's going on here. This relates the gravitational force between any two objects, objects M1 and M2, or object 1 and 2, and they have masses, right? And what this is saying is that this force depends on the two masses, M1 and M2. So if the masses are larger, the force is larger. If the masses are smaller, the force is smaller. But the force is also inversely proportional to the square of the radius. So there's a proportionality, there's a relationship here. So we can say force of gravity is proportional to the inverse of the square of the radius. You'll hear this called what's known as an inverse square relationship. where one thing is related to the inverse of the square of another thing. And that is what's going on here. As the radius increases, well, the force of gravity does get weaker, but so there's your inverse relationship, but it's inverse squared. So